Okay, let's continue. The next speaker will be Adolfo Guillot from Mexico. He will speak about foliated, affine, and projective structures.
Thank you very much for the opportunity of speaking here. And so this is a special session on differential equations and geometric structures. And I will really be speaking about differential equations and geometric structures. So I will be talking about holomorphic foliations in complex manifolds, and the problem of maybe the existence of some geometric structures going along the leaves of these foliations. Okay, so before going to, so I will report on some work done as a joint work with Bertrand Durand from the University of Cergy in France. So here's a picture of Bertrand. And so let me start discussing the situation of curves in of affine and projective structures on curves before going to the general setting of affine and projective structures along the leaves of a complex foliation. So I start with a complex curve. You know, so a complex curve, it has local coordinates taking values in the complex line, and the changes of coordinates are by holomorphisms. But we can restrict. We have these two groups. These are two of the three transitive Lie groups in dimension 1. So the first is just the group of affine transformations of the complex line as real geometry of R2 is just rotations and translations and homothéties, and these generate this group of affine transformations of the complex line. And we have this other group, the group of Möbius transformation of fractional linear transformations, PSL2C, that acts naturally on the extended plane, the complex projective line, the Riemann sphere, by fractional linear transformations. And if we have a curve, we can say that the curve is endowed with say a projective structure if we have an atlas taking values on the complex projective line, such that if I have two different charts, then the difference is given by a fractional linear transformation by the restriction of 1. So we restrict the group of changes of coordinates to projective transformations. And in this case, we say that the curve has a projective structure, or if we restrict it to the group of affine transformations, we say that the complex curve has an affine structures. So let me give some examples of these affine and projective structures, and please just interrupt me if you feel like it, if you want to ask a question or anything. So let me start with some examples of affine structures. Affine structures, not every complex, so I will be talking about compact complex curve, and not every compact complex curve admits projective structures. Only elliptic ones do. So let me give some examples of affine structures on the on elliptic curves. So the first one is when you construct the elliptic curve by taking the quotient of a lattice in C. And if you take the quotient of a lattice, well, you're acting by translations on the complex line, and the quotient is this torus. So you're naturally, the quotient is naturally endowed with a group of, with an affine structure, because we are acting by translations, which are particular instances of affine transformations. So this gives some examples. And there are other examples. Say, if you take in C -0, you take this map, Z goes to half of Z. And if you remove the origin, then you have a fundamental domain for this action that's the annulus, say between with exterior radius 1, interior radius 2, and you identify the two boundary components of this fundamental domain by an affine transformation. So in the quotient, you have again an elliptic curve, and this elliptic curve is naturally endowed with an affine structure coming from the quotient, coming from the natural affine structure in C. So these are different affine structures, but they both give affine structures in the sense I just defined. Okay, so let me now give some examples of projective structures on curves. So the most classical one is the uniformization. So you know that if you take, say, the Poincaré disk model of hyperbolic space, you can endow some curves by taking the quotient of your hyperbolic plane under some group of hyperbolic hyperbolic isometries of the plane. So this is a picture by an image by Arnaud Chérita doing this. So this is for the group of affine transformations, and this group, all these transformations that are isometries of the Poincaré disk actually extend to the whole projective line as projective transformations. We have here PU11, it's sitting inside PSL2C. So in particular, so this is more clearly seen in the upper half plane model, where you have PSL2R as the isometry group naturally sitting inside PSL2C. So if you have a hyperbolic structure, two-dimensional hyperbolic structure, you have, in particular, you have a complex projective structure in the sense I defined. So these are one kind of examples, and the uniformization theorem tells you that every curve, every higher genus curve, admits a projective structure such as the ones I described. Okay, so but these are not the only projective structures. All the structures given by quasi-Fuchsian groups give also projective structures. And let me just give one more example that's given by the Schottky uniformization. So consider, again, the Riemann sphere, and consider two sets of disjoint circles, here and here. And we're going to do more or less what we did with the torus and for the affine structures, and we're doing this in 2 times. So take the complement. So these 4. I have these 4 disks in the Riemann sphere. Just remove them, and then glue, identify the boundaries of the blue pair in this way. So we have a loxotomic transformation. So these 2 circles can be identified. These 2 blue circles can be identified by a Möbius transformation. So that if you exit, and if you go in this way, you can come back this way. So you don't really exit the curve. And if you do, so you identify these 2 boundary components in blue by fractional linear transformations, and you do the same of the 2 boundary components with the red curves. You get a genus 2 curve. In this case, you can get any genus you want by identifying these boundaries. The group behind is one of these groups called Schottky groups. And so these are other kinds of groups that are not given by the uniformization, or that are not even close to uniformization. So these are more examples of projective structures. Okay, so good. So let me tell you about how many projective structures we have on a given curve. And for these, let me recall that we have this differential operator, the Schwarzian derivative, that is particularly well adapted to Möbius transformations. One of the properties has very good, it is intimately related with the group of fractional linear transformations. The Schwarzian derivative of such transformation vanishes, and it has very good change of coordinates properties. So we are still in curves. So if you have two projective structures on a given curve, so you have these, let me just put one in one projective structures, and then let me give a chart of this projective structure. And I have a different projective structure, say in green. So in the change of coordinates, if these two projective structures are different, you do not have a fractional linear transformation, but you have nevertheless some map between open sets in the projective line. And these maps, well, are not fractional linear transformations. So, but you can nevertheless evaluate the Schwarzian derivative along this of this map. This will be so this Schwarzian derivative gives you a quadratic differential. So in this way, you can measure the difference of two projective structures as a quadratic differential locally. And in fact, this quadratic differential will be globally well defined. Okay, so we can say this. So if we take two projective structures, the difference will be a holomorphic quadratic differential on our surface. And in this way, when you put in together the properties of change of coordinates of the Schwarzian derivative, you get that over a given complex structure, the space of projective structures is naturally an affine space directed by the directed by the vector space of quadratic differentials. So in particular, if you have a genus 0, you get just a point. You get no quadratic differentials. If you have genus 1, this space of quadratic differential will have dimension 1. And for a higher genus, you will have a space of dimension 3g minus 3. Okay, so we have a very nice picture. We have a complete picture, at least as far as the existence of projective structures is concerned. So all complex curves admit projective structures, and the projective structures form an affine space, and we know exactly the dimension. So this is, of course, just the beginning, because if we want to understand projective structures, we will have to understand particular cases. What does any particular structure look like? Understand. So this is just the beginning, but this is just the existence of what I'm speaking about. So I said before that the existence of projective structures is guaranteed by the uniformization theorem, but using the Schwarzian derivative, there are some cheaper ways of guaranteeing the existence of projective structures. So let me briefly tell you what this is. So I'm still talking about curves. Okay, so let me tell you what this is. Okay, so this is an argument due to Poincaré of this existence of projective structures. So take a curve and endowed with a complex structure. So you have charts taking values in C. And whenever you have two charts in intersecting domains, so you have some map going from one open set of the Riemann sphere to another one, which is not necessarily a fractional linear transformations. If they were fractional linear transformations, we would have a projective structure. So this is not a fractional linear transformation, but we can nevertheless take the Schwarzian, as defined in the previous slide, the Schwarzian of this change of coordinates. So this gives us naturally a cocycle in Czech cohomology, and this defines naturally some class H1 in our curve with values in the space of forms of quadratic differentials in our curve. So it is easy to see that if the cohomology class of this cocycle vanishes, if and only if we can modify these charts we're given by some, we can correct them by some mappings in order to get compatibility. So actually this is by cell duality equal to the H0 of C with values in the tangent of C. So so let me say this again. So there is a natural class here in this cohomology, Czech cohomology group, given by the complex structure, and this cohomology class vanishes if and only if our curve admits a projective structure. Okay, so in particular, since by cell duality we have these that is equal to the H0 to the space of holomorphic vector fields, these proofs, this gives it a less complicated proof of the fact that every higher genus curve admits a projective structure. Okay, so this is as far as affine. So this is all I want to say. There's many things to say, but this is all I want to say about affine and projective structures on curves. So I don't know if there's any question so far.
I have one stupid
Sure.
question. So first, what fails to do this same argument with affine? Just say taking instead of Schwarzian some nonlinearity or something like that derivative.
Yeah, the same thing. We have the same thing. We have also for affine structures, we have some class in H1. This will be in with values in the space of forms, and everything I said for with respect to quadratic differentials works in the affine case with respect to just differentials, just one forms. So it's perfectly analogous.
Okay.
Okay, so this is everything I want to say about curves. So let me go now to foliations. I will be speaking about holomorphic foliations by curves on compact manifolds. So suppose you have some, so let me just recall what we mean by a holomorphic foliation by curves with singularities. So Claudia was telling us about some of these in the last talk. So what I mean by a holomorphic foliation by curves in a manifold, so we have some manifold M, and I want to have some cover of M, and in each open set of the cover, I want to have a holomorphic vector field. So I have UI, and I have a vector field ZI, which might have singularities. And I want to glue this, this together, but in such a way that in UI intersection with UJ, we have that the vector field ZI is some Gij Zj that is proportional. So they have the same, they define the same integral curves, probably parameterized in a different way with this Gij, this function from UI intersection UJ to C minus 0. Okay, so this is what I'll mean by a holomorphic foliation by curves. And so this this Gij, they form a cocycle, and they define one line bundle on my manifold that is naturally associated to the foliation, which is the tangent bundle, the tangent line bundle to the foliation. Okay, so we have this natural line bundle associated to the foliation. We have its dual, that's usually called the canonical bundle of the foliation, and it's the space whose sections are the one forms along the leaves of the foliation. Okay, so this is what I mean by foliation by curve. And so I want to talk about foliated, affine, and projective structures of manifolds. So along the leaves of the foliations. So what do I mean by that? I mean, I have some manifold and I have a foliation, which might have some singular points, but this definition does not involve explicitly the singular points of the foliation. So what's a foliated? So let me tell you what a foliated projective structure is. It's just, well, you take some maps of that will be the charts into C, such that these maps are in restriction to each integral curve are just if I restrict these maps to some integral curve, they give exactly these are holomorphic maps, and these holomorphic maps give, when restricted to each leaf, an affine or a projective structure. And that's what I mean by an affine, foliated, affine, or projective structures. So you can say that it's just a foliated structure on each leaf of the foliation that varies holomorphically in the transverse direction. Okay, so these are foliated. So this is what I mean by foliated. So we want to understand these. These appear very naturally in many settings. For example, in the setting of translation surfaces, the period foliation has naturally a translation structure along the leaves. We have already used with Giulio Rebello in some of our work on univalence of solutions of differential equation. We used some leafwise affine structures, and then they appear naturally in this problem of isomonodromic deformation, some natural projective structures along the leaves of some foliations appear naturally. So we wanted to understand better to give us a framework and some results concerning these more general foliated affine projective structures. So let me give you just two examples where these foliations appear. So foliations on the complex projective spaces are given in this way. So we have here Pn, the complex projective space, and all the foliations here are built, as Claudia tells us about in the last talk, by a homogeneous vector field on Cn plus 1. So we have here Cn plus 1. We have, and consider Z a homogeneous vector field. So this homogeneous vector field will have some integral curves. And in fact, these curves will be invariant by the action of homothéties on Cn plus 1. So if I act by some homothéties, I will preserve the integral curves. And so when I take the quotient, I will induce some foliation on Pn. There will be some lines that pass through the origin that will be some orbits of this homogeneous vector field, and this will project onto singular points of my foliation. Okay. So this is what a foliation on Pn can be described also in this way. This is what it looks like. And in fact, when I do this homothéty, I not only change that one integral curve to another one, but I do so affinely if I consider the natural coordinate given by the solution as a differential equation. So not only I act, I not only map curve to curve, but I do so preserving an affine structure. So each time I describe homogeneous vector field, foliation on Pn as induced by a homogeneous vector field on Cn plus 1, it naturally inherits leafwise affine structure varying holomorphically. Okay, so this is one source of example, and all it turns out that all foliated affine structures arise in this way for foliations on Pn. And let me give you another example. This is Hilbert modular surfaces. So if I take the disk, the unit disk D and C, I can take in D cross D, I can take some group in the inside the automorphism group of the surface D plus D. I can take some group, and if this group is not proportional to a lattice to a product of lattices, we have such groups. Then it will act. There are some groups that act on D cross D, which are not virtually product of lattices, and which act on D cross D with a compact quotient. So this is D cross D. So they will act, these groups, preserving both the horizontal and the vertical foliation up to finite index. So in the quotient, we have some manifolds that are naturally endowed with foliations. And since the group of automorphisms of D preserves naturally a projective structure, I will have that both of these foliations have naturally at leafwise projective structure varying holomorphically in the transverse direction. Okay, so these are Hilbert modular surfaces, and these give other examples of foliated projective structures. So the natural question is, well, what about the existence? Does every foliation support a leafwise projective structure? Affine. What are the obstructions? What do we know about this? What's the situation? Okay, so I told you before that for curves we naturally have a class, a cohomology class given by in the H1 of the curve with the values in the space of quadratic differentials, and we have the same obstruction at the level of foliations. So if you have a foliation by curves with singularities on my complex manifold M, we have this class in this H1 of my manifold with values in the sheaf of quadratic differential along the leaves of the foliation. And this class vanishes if and only if F supports a foliated projective structure. So the construction is exactly the same as the one I told you before. But so in general, this is difficult to calculate. So we don't really know, we know little, we have very few examples where we can calculate this class explicitly. So let me give you examples of where we can calculate, instances of settings where we can calculate this example. I know if there's a question.
Sorry, K2 is the line bundle of quadratic differentials?
Yes, so KF is just the dual of my tangent bundle. So it's usually called the canonical bundle of the canonical line bundle of the foliation. So this K squared is the quadratic differential, is the sheaf of quadratic differentials along the leaves of the foliation.
And what happens at the singularities?
So I forgot to tell it, but so I'm in my definition of foliation, my local vector fields generating my foliation are supposed to have at least codimension 2 singularities. So I'm not imposing any restriction at the level of the explicitly at the level of the singularities, but you have some Hartog's phenomena that tell you that you do have things at the singular points.
So this KF is a line bundle?
This KF is a line bundle on the whole foliation. Yes. So it has local sections even at the singular points of the foliation. So the holomorphic, so you should, for example, for the tangent, well, you know this better. So Javier, so if the tangent bundle, so the local sections are just the tangent bundle of the foliation, its local sections are the vector fields generating the foliation. So even if these vector fields have singularities, these will not be singular points as sections.
So in CP2, this is always 0.
Yes. So
one of any line bundle in CP2 is 0.
Yes, and every line bundle in every foliation in CPN has an affine structure by what I just said before, and it has in particular an projective structure.
Thank you.
Okay, so generally this is difficult to calculate. So for example, we are able to calculate this class, and we know that this class vanishes, for example, on any holomorphic foliation on the product of your projective line with any curve C. So if you have this all these surfaces, any foliation in any foliation we can calculate this obstruction and it will vanish. Okay, so this is an example where we can guarantee the existence of foliated projective structures by calculating this obstruction. And we also have cases where where this obstruction has been calculated for more general projective structure. So this concerns the notion of Kodaira fibration. So these are surfaces, compact complex surfaces that fiber over a curve, whose fiber is also a curve. So this is non-singular. So I have a fibration, C infinity fibration, locally trivial fibration, which is not a holomorphic fibration. The fiber varies as a point in the base varies. So this is a Kodaira fibration, and Sheng-Juan Shao has calculated, essentially has calculated this obstruction, and he has shown that this obstruction by some very beautiful classical geometry, he has shown that in this case that the obstruction does not vanish. So this gives us no Kodaira fibration will admit a foliated projective structure with respect to the foliation given by the fibers. In other ways, there is no way in a Kodaira fibration of assigning a projective structure to each fiber varying holomorphically along the base. Okay, so this is a very nice result by Sheng-Juan Shao. Okay, so it's difficult to calculate. So in some sense we have an answer because we know exactly when we know exactly what the obstruction is, but it's an obstruction that is difficult to calculate. Okay, but we do know some other instances of. Let me give you some instances of in surfaces of foliations where we can explicitly say whether it admits or not a foliated projective or affine structure. So we know, for example, that elliptic fibrations admit foliated affine structures. We know that we may have singular curves, but we know that on the regular curves we have some canonical affine structures given by integration of one forms along the curve. And in fact, this affine structure on the regular curves extends to the singular curves. We know also that some foliations on some non-Kähler surfaces admit foliations, like on Hopf, Inoue, and Kato surfaces. And these are interesting, but because they tended to be unique, these affine structures. We also know that all foliations on Calabi-Yau surfaces, like abelian K3 surfaces, admit foliated affine structures. So here, what we do to obtain them is, we have some the canonical bundle here is trivial, and we have some connection because it is trivial. We have some flat connections on these line bundles, and we can think of these connections as restricting them along the leaves of a foliation. Okay, so we have some connections, and we have this classical bot connection that only takes place along the leaves of the foliation, and it leaves this bot connection is a connection on the cotangent conormal bundle of the foliation, and if we do some adequate powers and combinations of these two line bundles, these connections will live on the we can get to the tangent bundle of foliation and produce a connection on the tangent bundle of the foliation. which will be necessarily flat, which will give us a connection on the tangent bundle along the leaves, which is the same thing as an affine connection. So for projective bundles, so for projective connections, so this is the way in which we can prove the existence of foliated affine structures on Calabi-Yau surfaces and in general on all Calabi-Yau manifolds. So for projective, so these are affine, in particular projective, and we are able to prove the existence of projective structures on, for example, suspensions or turbulent foliations, or as I said before, foliations on product of a curve with C. Okay, so in some cases, these are by construction, in others by calculating the obstructions, in others by calculating some facts about connections. And but for example, we don't really know for ruled surfaces. So we don't know if all foliations on ruled surfaces admit foliated projective structures. We think that is the case. It's probably not that difficult. And you should start by reading Javier's article about the foliations on ruled surfaces. So we've done so for. Okay, so I will not tell you. So this is this question. I think it's an interesting one. Okay, so one of our results is an index theorem for such kind of foliations. And before telling you a more abstract way, let me give you a concrete, in a concrete way, what our index theorem says. So start in P2 and consider the foliation given by the pencil of curves passing through 4 points. Okay, so we have some four singular points, and I will consider the foliation given by the pencil of these conics. Okay, so individually, each curve is a rational curves with 4 marked points, which are these 4 points. And we have some degenerate curves, which are given by the, so some degenerate curves in the pencil are given in this case by when these conics degenerate into the union of 2 lines. So we have 3 special curves coming by the 3 ways into which these 4 points can be taken in pairs. So the general curve is just some curves with 4 marked points. The cross ratio varies. And suppose you have some a foliated projective structure along the leaves of this foliation. It means that you have, in particular, for each one of the integral curves, you have a projective structure. And when you consider this as a projective structure in a curve, you will have some singularities. So if you will have along these, in the neighborhood of these points, you will have some degenerate projective structure, but it turns out that you will have some index nu, so that the projective structure is locally given by the map z maps to z to the nu, and this index is well defined. Okay, so you have for each one of the 4 points, you have some nu1, nu2, nu3, nu4, and it turns out that these indexes nu1, nu2, nu3, nu4 are independent of the curve. They agree at the points. So at the points, all the curves that pass through a given point will have the same index, nu1, nu2, nu3. Okay, so these are 4 indexes that appear in a foliation. And remember that we have 3 curves, 3 special curves, that these are when the conic degenerates into a product of lines. This happens because there's some curve that gets pinched in our curve. So this we'll have some curve here that will be pinched. And as the curve gets pinched, you will get this singular point. And the singular point will also have some index corresponding essentially to the monodromy of this projective structure on the curve. That let me call this mu I. Okay, so we have 3 pinchings that occur, and each pinching has one index, some index called mu I. So what our index theorem will say in this case is that if we take the sum of 1 over mu I squared, this will be equal to 1 plus the sum of 1 over mu I squared. So these three pinchings are not independent, and we have an explicit algebraic relation relating the indexes of the structure at this pinching. Okay, so we have so this is so I will give a more general statement now, but this is what we mean. We have some oh, okay, I'm running out of time. So we have some pinching of so we have one global relation between some local data of our foliation. Okay, so I wanted to give you this explicit example, and let me give another instance of the theorem, one where there are no singular points involved. Okay, so this is a special case of this index theorem. So for regular foliations. Okay, so you suppose you have a compact complex manifold and you have a foliation F, regular. This case, in order to simplify, I'm omitting the singularities, but the general case has the singularities. And suppose you have a regular foliation by curves, and then you have a leafwise projective structure. Okay, so we have these line bundles TF. We're talking about them, and so these line bundles have some Chern classes, which live in H2 of our manifold. And so this index theorem will tell us something about these Chern classes when these foliations admit projective structures. So if our manifold is of even dimension, we can prove that the top exterior power of this Chern class vanishes. Okay, and when n is odd, we have that this power of the Chern class together with this Chern class of this virtual normal bundle of the foliation will be 0 as well. So more generally, I will not put the more general statement. We have some results that concern more general Chern classes of the tangent and virtual normal bundle of the foliation on one hand, and on the other, some local data of our foliation that concentrates on the singular point, as in the previous example. Okay, so this special case of index theorem, so the general index theorem is obtained by applying the Baumbach index theorem to some special foliation that we build from our original foliation and the projective structure. We have, in some sense, some in the same way as Riemannian metric on a manifold gives you a geodesic vector field. So this projective structure along the leaves of foliation will give us, in some sense, a foliated geodesic vector field. And if we construct some appropriate compact manifold where this foliated geodesic vector field lives, we can apply the Baumbach index theorem and then try to interpret what we get in terms of the foliation on the base. And in this case, we get an index theorem. Okay, so let me give you some consequences of this index theorem. So the first one is that if you have a compact complex surface and you have a holomorphic foliation, let me do it just in the case where we have a regular foliation with no singularities, and if you admit a foliated projective structure, then your manifold has vanishing signature as a real dimensional four manifold. Okay, so in particular, this gives another proof of Shen-Yuan-Xiao's result, because Kodaira fibrations always have non-trivial signature. So our result implies that it has vanishing signature. No Kodaira fibration can admit foliated projective structure. But also, if you have a surface of general type, and you have a foliation that is not a fibration, and it carries a foliated projective structure, then automatically your manifold will be a quotient of the pi disk, and your foliation will be a Hilbert modular foliation. Okay, this last corollary uses the classification by Brunella of regular foliations of surfaces. We do not really know if the existence of a foliated projective structure is necessary for the conclusion, but in any case, we have this corollary. And a second corollary is in all dimensions, in uneven dimensions. So you have, suppose you have a regular foliation on an even dimensional surface, and you have a foliation regular, and that is of general type in the sense of this Mendes-Brunella-McQuillan classification. This is that its canonical bundle has lots of sections. Then you may conclude that this foliation does not support a foliated projective structure. Okay, so so these index theorem, I think it's interesting in its own right, but it also helps us give obstructions to the existence of foliated projective structures that are easier to calculate than the cohomology class I was talking about in the first case. There are, however, some foliations that do not fall within that, where we do not get any information from our index theorems. So let me give you one large class. So suppose you have a symplectic manifold of dimension 4 complex, and you have a codimension 1 smooth hypersurface S inside the conclusion. The inclusion is the other way around. So your symplectic foliation, your symplectic form, its kernel will induce foliation by curves on this threefold S. And for this foliation, our index theorems do not give any information whatsoever, and we do not know if these foliations admit foliated projective structures. So, so we do not know anything about this. I think that these are interesting. So, and in general, our results tend to work better in even dimensions and less better in odd dimensions. So we know that these foliations, for example, do not admit foliated affine structures, but we do not know if they admit foliated projective ones. So let me finish just by stating that, like putting here some references. This is our preprint with Bertrand, and then there are some Sheng-Marshall's result about Kodaira vibrations is in this preprint, and in the last reference is Sheng-Marshall applies our result on the inexistence of foliated projective structures on one of the ones on Kodaira vibration on surfaces of general type, that they are necessarily Hilbert modular vibrations, foliations. He applies it to the classification of these birational Kleiner groups. So thank you for your attention, and if there's any questions, go ahead.